Okay, this problem is a simple dehydration one. If you're sweating a lot and you're not drinking fluids, you're going to be dehydrated. That's going to lower your the volume of your blood. Looking at capillaries, just in general with the circulatory system, if I draw a capillary here, a weird capillary, we've got three pressures acting on it. We've got the hydrostatic pressure, which is the pressure of the blood based on the volume pushing against the sides of the blood vessel, trying to get out. The next two are oncotic pressures. We have our BCOP, which is our blood oncotic pressure, as defined by the number of solutes in the blood compared to, we compare it to no solutes outside the blood. How much pressure the fluid is exerting to come in to the blood vessel to equalize the osmolarity caused by the solutes. And the third is the interstitial oncotic pressure. This is how many solutes are outside the blood vessel compared to inside, meaning it is the pressure of how much fluid is trying to leave the blood vessel to establish equilibrium and osmolarity. If we're dehydrated, the thing it's going to affect most is the hydrostatic pressure. You might be thinking that, oh, if your blood volume decreases, then your BCOP must increase, thinking there's the same number of solutes. And your thinking is right, but if you were given a multiple choice answer on an exam and you had BCOP as one of your answers, BCOP increasing, the most correct answer would still be hydrostatic pressure. That's what's affected the most. What's happening in tissue capillaries compared to normal? Well, hydrostatic pressure is trying to force stuff out. And so if that decreases, then not as much is going to leave, not as much fluid is going to leave the blood. So less fluid. How would the kidneys respond? Looking at the kidneys is a little bit of a different setup because we have our glomerular, capillary inside of Bowman's capsule, and then this goes all the way down and all the way back up, and then we've got some macula densa cells. As less fluid leaves, less sodium and chloride are going to go down and back up, and these cells are going to evaluate the levels of sodium and chloride, and if they're too low, meaning if it senses a low filtration rate, it's going to raise it, the GFR. So we know immediately that all these are wrong because they all say lower. But let me explain a little bit. An easy way to remember which one is afferent and which one is efferent is A comes before E. Let me grab a different color because I'm getting tired of black. A comes before E. That's the afferent, that's the efferent. So the efferent arteriole will contract. If this contracts, then blood is going to get backed up in the capsule and we will end up raising GFR. So this statement, G, is simply false. Contraction of the efferent arteriole will raise GFR. Likewise over here, if this arteriole relaxes, it lets more blood in and it'll raise GFR. So those two statements with lower are just false. They need to be raised if they're going to be true. Then the macula densa cells can release nitric oxide onto the afferent arteriole and raise the GFR. Nitric oxide causes the afferent arteriole to relax. That's what it does. And that's how it raises the GFR. Let me just label these. These are macula densa cells. They can also lower GFR by releasing adenosine, but we want to raise it. So the correct answers are D, F, and I.